Hello and welcome to this video lesson. In this video lesson, we will be looking at an example of a projectile motion question. We got a football match happening, and in this football match, Albert throws the ball at a speed of 18 meters per second at an angle of 30 degrees above the horizontal. Mary makes a jump and receives the ball in the air 25 meters away horizontally from where it was thrown. What we want to do is calculate the height relative to the initial throw where the ball was received and the velocity just before Mary catches the ball. Let's start by drawing a system diagram for this situation. So we got Albert first, and Albert throws the ball, and the ball goes at speed of 18 meters per second. And travels, and Mary here jumps up and receives the ball somewhere. And basically some of the stuff that we need to figure out is the height at which the ball was received. So we're kind of looking at that height, which is relative to this point over here. And we want to figure out at what speed was the ball cut, or velocity just before she actually catches it. So it will actually be a vector quantity. Let's put all the informations that we have. So basically we have this 18 meters per second. We know that it's 30 at an angle 30 degrees from the horizontal, so I'm going to put that in. I am going to put in my acceleration downwards as I'll use 9.8 for this example, and acceleration in this direction is 0. We're going to assume that there's no air resistance. I'm going to have to break this into v1x and v1y, and I'll do that in a little bit. I know that the ball is going to be received at some sort of velocity, so right at the very end here we're going to have velocity 2 x, and we're going to have velocity 2 y. And for now, just because most of my actually, you know what? I will put it down as v2y in the downward direction. Good. So we got v2y, v2x. We got the accelerations. Let's do the displacements as well. Displacement in the x direction starts here and ends right here. And I'm going to use that as displacement in the x direction. And displacement in the y direction I actually have done already. And that's over here. Displacement in the x direction is given to me as 25 meters, so I'm going to label that, and this one isn't. v2x is going to be same as v1x, just because there's no air resistance slowing it down in the x direction. v2y we don't know, we have to calculate. I'm just going to leave it empty at the moment. And delta t is the final thing. And we don't know delta t either, so we might have to calculate it depending on the situation. Since the initial velocity is given to us in terms of a vector, we need to break it down into the x and y component. What I'm going to do is I'm going to choose a coordinate system, and since many things are pointing downwards, I'm going to use this as my positive x and this as my positive y direction. And I'm gonna bubble this in because I'm gonna be using it throughout this whole question. And I'll do a nice little green highlight here. Delta t here is also unknown, so I'm just gonna put a question mark. And to break down the vector for the initial throw, I'm going to redraw it here, and I'm going to have the x direction and I'm going to have the y direction. I know that this is 30 degrees. I know that the magnitude of the velocity or the speed here is 18 meters per second. So now I have to find the speed. So I'm just going to move this up a little bit. I am going to find the speed in the x direction. So this is v1x and this is v1y. For v1x is adjacent to my angle. So v1x using SOHCAHTOA will end up being the hypotenuse multiplied by the cosine of 30. And v1y will equal to 18 times the sine of 30, just because it's opposite to my angle. So this one is opposite, we're going to use sine. This one is adjacent to the angle, so we're going to use cos. Using my calculator, v1x ends up being 15.588 and it's going to continue on, so I'll just round the last digit, and 18 sine 30 is going to be 9. And the units for these are meters per second. This is meters per second, and direction in the x direction, it's going forward or in the right direction, and in the y direction, it's going up. So I'll put those as well so that later on I can actually relate it to my coordinate system when I'm plugging them into my kinematics equations. Okay, let's see what informations we have and what we can find. Let's look at the y direction first. In the y direction, I have my v1y value. That's here. I don't have delta t. I don't have dy. I do have my acceleration, so that's two pieces of information. I don't have displacement in the y direction, nor the velocity. So therefore, I actually can't do anything in the y direction because I always need three pieces of information in order to find the other two. Therefore, I have to go to the x direction, and hopefully I'll have enough information in that direction. I'm going to use the lovely color of green here. In the x direction, I do have the velocity. The velocity isn't changing since there's no acceleration, and therefore I can use the average velocity equation, which states that average velocity, because it's constant, is equal to the displacement over time. In this equation, since again I have the velocity and I actually have the displacement here, then I can actually solve for delta t, or the change in time. So the change in time, if I were to rearrange this equation, will become the displacement in the x direction over velocity average. And when I'm plugging in my numbers for delta x, I'm saying that from position it moves from position 1 to 2 in this direction, in the right direction, and that's in my positive direction. So I'm going to use a positive value there. And my velocity is, my velocity 1, which is not changing, is also in the right direction. So I'm going to use a positive value there, which is nice because both are positive, and that means the time will end up being a positive value. And if it was negative, I would know that I have made a boo-boo, and in this case I know that I have not. Once I plug this into my calculator, I will get my time as 1.604, and I'm just going to round it to this for the time being. And when I will use it in the next set of calculations, I will use the exact value of my calculator. Now this is fantastic because now I have the time as well, and since I have the time, now I can start calculating everything else. The first thing that I'm asked to calculate is the height above which the ball was thrown, at which it was caught, so that's delta dy. So I will circle delta dy, which is the displacement in the y direction, and I will look for an equation which would have the initial velocity in the y direction, delta t, the displacement, and finally acceleration. The appropriate equation to use is going to be displacement is equal to v1 delta t plus half a delta t squared. And this equation has displacement, initial velocity, change in time, and the acceleration. I'm not going to write delta y every time. I'm just going to label delta y here, and I'll do all my calculation in the y direction here. I'm just going to write it in orange as well to help you visualize this a little bit easier. So delta position here is equal to v1 y, which has a value of 9. But notice that my y positive is in the downward direction, and this is actually in the upward direction. So I have to use a negative value here. That's negative 9. Delta t is approximately 1.064. Again, when I plug it into my calculator, I'm going to use the exact value that I got here in my calculator and not the estimated one here. Plus half. For acceleration, I'm going to use 9.8 and 1.604 squared. The value that I get is negative 1.83087, and I'm going to approximate that with, I believe, 2 significant figures because of my values, as 1.8 meters. And in terms of direction, so looking at my coordinate system here, down is positive. So since I get a negative value, that means it's not down, it's actually up. So I'm going to put an arrow in the up direction as my direction, and that makes sense because, or in this case, Mary has jumped to catch the ball, and if she has jumped, it would make sense that she's caught it 1.8 meters above the initial throw. This is a little bit unrealistic in terms of jump, but we can assume that Mary is very, very, very strong and she can actually do a jump that high. Since I have answered the first part of the question, I'm just going to make sure that I have a proper format here. This is change in the y direction, and I'm going to box my answer, and I'll just add a highlight to it as well so we know that that's our first set of answer. The second part of the question is asking what is the final velocity, or velocity just before Mary catches the ball. In order to do this, we need the final velocity both in the x directions and the y direction. So in the x direction, we already know what the value is. We need to find it for the y direction. In the x direction, the value doesn't change, and we already have that right here. v1x is equal to 15.58846, and that's same as v2. So I'm just going to move up a little bit, and I'm going to write that down. I'm going to write that. I'll do this part of the question. Actually, I'll still write in green because that's information from the x direction. Put a line through here. v2x is equal to 15.58846 meters in the east direction, or sorry, in the right direction. And for v2y, we actually have to figure out what the value is. We have at least 3 pieces of information. We actually have 4 now, so we can actually make that calculation. We can use any of the 5 kinematics equation, but I will be using, and I'll write everything here, v2y is equal to, so the final is equal to the initial speed plus the acceleration in the y direction multiplied by delta t. To plug in my values, v1y is 9 meters per second. So I'm going to put my positive directions again. And I'll move everything up so we can see things a little bit easier. in terms of my direction, down is positive, and since the initial speed is in the up direction, I'm going to put a -9 plus. My acceleration is in the downward direction, and that's same as my coordinate system over here. So I'm going to put 9.8, and delta t is approximately 1.604. And when I put that in my calculator, and I'm using the exact value from my calculator, I'll put 3 dots here because that will be a little bit more precise. I get 6.71675 ... And I'm going to use that exact value when I'm calculating everything for the final vector. The direction for this is, since this is positive, and in my coordinate system, positive is moving down, therefore this is also going down, and that's the speed, meters per second. And I should fix this unit as well, and this is also meters per second. Okay, now let's combine everything and figure out what our final velocity is. I'm going to move up a little bit so we have a little bit more space, and I'm going to use green for my x value. My v2x is 15 meters in the right direction, so I'm going to draw that like this. And the magnitude of this is 15.588. And my y component of velocity is going downwards, and it's got a magnitude which is smaller than 15. It's 6.71675. So I'll write that, and I'm going to do the final solution in purple. And my final vector starts from the initial point and goes to the very end. And this is going to be my final velocity. And here's going to be its angle. To find the magnitude of v2, I'm going to use Pythagorean Theorem, which states that v2 squared is going to equal to 15.588 squared. And again, when I'm putting things in my calculator, I will use the exact same value as I saw in my calculator and not actually round them. And when I do this and I take the square root, I will get 16.9739 as my speed. And this is meters per second. I also have to find this angle over here, and this angle theta. I have my opposite and I have my adjacent, so I'm just going to use the tan rule, which says tan theta is equal to opposite, in this case 6.71675, over my adjacent, which is 15.588. And once I take my inverse of tan, I get approximately 23.3 degrees. Finally, I have to show my results as a vector. So final velocity has a magnitude of approximately 17 meters per second in the direction. And for my direction, I will go in the east direction first. So I'm just going to show you folks here that I'm going in, not the east direction, but I'm going in the right direction, turning 23 degrees towards the downward direction. So this is 23 degrees down. And this is my final velocity. And I'm going to highlight it, and I'm going to box it, and I'm also going to highlight it. Now, in terms of whether the answer makes sense or not, we always should check to make sure that our answer makes sense. 17 meters per second, it was thrown at, initially, looking at the question, it was thrown at 18 meters per second, so it's caught at a little bit lower speed, which completely makes sense. If you look at the trajectory, it's going up here. In the speed in the x direction isn't changing, but the y the velocity in the y direction is actually reducing when it gets to the maximum height and starts speeding up a little bit. You can see that it speeds up in the y direction, but it doesn't reach the same height that it was thrown. So the y component is a little bit less than the y component that it was thrown out. So that makes the final speed slightly lower, and in this case, that's exactly what we observed. In terms of our angle, initially is 30 degrees. Our final angle is 23 degrees, so slightly less, and that makes sense. We know that when it comes back right at this point, the angle should be exactly 30, and before that, the angle is going to be less. And in this case, it's a very short distance, and the 23 degrees actually makes sense. So this is how we can solve projectile motion questions. Make sure that whenever you're doing this, that you always draw a system diagram, especially when you're beginning to do these questions. It's much easier. Make sure that you have a coordinate system, and make sure when you're plugging the numbers within your equations that you're entering them correctly based on your coordinate system. And if you do, all your answers should make sense. Also know that whenever you have 3 pieces of information, you can always find everything else. And in the x direction, if there's no air resistance, you can always use this equation over here, which states that average velocity is the displacement in the x direction divided by the change in time.